Okay, let's dive right into this explainer on a seriously fascinating new framework from USDC CMI called ARAG. This is something that promises to completely change how AI models interact with data. If you've been paying any attention at all to the frontier of large language models, you know they are getting incredibly good at complex reasoning. But when it comes to pulling in external knowledge, a process we call RAG, or Retrieval-Augmented Generation, they've been kind of curiously held back. So today, we're looking at a huge breakthrough that finally hands the steering wheel over to the AI itself. So here's the big question we're exploring today. Why are our most advanced language models, the ones that have these amazing reasoning skills and can execute really long horizon tasks, still being forced to use rigid, predefined retrieval workflows? It's honestly a bit like hiring a brilliant, world-class detective, but then forcing them to read a suspect file strictly page by page from beginning to end, rather than just letting them jump around and follow a hunch. Basically, the pure intelligence of the model is being bottlenecked by the sheer inflexibility of the search process.
Here is what we're going to cover today. First, the problem with current RAG. Second, the Agentic RAG solution. Third, the 3 hierarchical retrieval tools. Fourth, how it's shattering benchmark records. And finally, the future of AI agents. Let's get to it.
All right, part 1, the problem with RAG, specifically looking at static LLM pipelines.
So, why exactly are the old-school traditional RAG approaches struggling so much to scale? Well, it really comes down to fixed paths. Traditional methods like naive RAG, graph RAG, or workflow RAG basically do one of two things. They either retrieve a huge bunch of passages in a single shot and just dump them all into the model's input, or they use a super rigid pre-programmed workflow. It's exactly like a researcher being handed a massive stack of random pages and being told to just figure it out all at once. Agentic RAG, on the other hand, gives the model the freedom to explore autonomously. It actually lets the model itself decide when enough evidence has been gathered to finally answer a question.
Which brings us to part 2, the Agentic RAG solution and the ARG framework. What makes ARAG so special is that it is the only paradigm right now that satisfies 3 very specific principles of true agentic autonomy. First up, autonomous strategy. This means the model itself decides when to retrieve, what to retrieve, and exactly how to retrieve it. Second is iterative execution, which allows the model to loop, taking a multi-step approach through a problem, adapting on the fly based on what it just uncovered. And third, interleaved tool use. This follows a React-like framework, meaning the AI dynamically alternates between reasoning about a problem and then actively acting on it. The AI is fully in charge of the whole shebang.
Think about it like being a really smart researcher in a massive physical library. A human doesn't just blindly pull 50 books off a shelf and try to read them all at the exact same time, right? Instead, we systematically search catalogs for exact titles, we browse through conceptual summaries, and only when we find exactly what we need do we pull a specific book off the shelf to read one targeted paragraph. The researchers here realize that information in any given dataset is naturally organized at multiple levels of detail, so the AI needs tools that actually match that human-like hierarchical searching.
So let's look at those tools in part 3, hierarchical tools and multi-granularity.
The very first tool in the agent's tool belt is keyword search. This is basically your exact title lookup. It retrieves abbreviated snippets where specific keywords appear. And what's cool is the researchers explicitly avoided heavy pre-indexing here. Instead of building these massive, incredibly complex knowledge graphs offline before you even start, this tool just performs exact text matching right at query time. It's super fast, it's lightweight, and it's absolutely perfect for when the AI knows the exact name, date, or entity it is looking for. But what if the exact wording is unknown? That builds directly into the second tool, semantic search. The agent uses this when it needs to find conceptually similar sentences. It uses dense vector representations, which is a fancy way of saying it searches by mathematical meaning rather than exact spelling. So if the AI's keyword search totally failed because a document used the word automobiles instead of cars, semantic search steps in to bridge that conceptual gap. It finds those connections and returns the top-ranked sentences, cleanly grouping them by their parent chunks.
And finally, tool number 3 is chunk read. In RAG, the entire database is partitioned into semantic chunks of about 1,000 tokens, which is roughly a couple of pages of text. The model only ever uses chunk read when it has successfully found the right snippet using the previous 2 tools, and now actually needs to read the full context to extract an answer. Instead of just indiscriminately loading massive amounts of context all at once, the agent incrementally retrieves information strictly on demand. It can even read adjacent chunks if the information spills over a boundary.
Now here is a really clever, ingenious feature built right into this loop.
the context tracker. As the AI explores the data, this mechanism tracks exactly what has already been accessed. If the agent tries to use chunk read on a piece of text it has already seen, the tool simply kicks back a message saying, "Hey, this chunk has been read before," and it consumes 0 additional tokens. This forces the agent to explore completely new, diverse parts of the database, rather than getting stuck in an infinite loop reading the exact same passages over and over again.
All right, moving on to part 4, benchmark records. Let's talk state-of-the-art performance. The results here are honestly staggering. The researchers put this to the test on multiple multi-hop QA datasets, and ARAG achieves state-of-the-art performance across the board. When we look at the Hotpot QA benchmark using the GPT-5 mini backbone, GraphRag hits 82.5%, HippoRag 2 hits 84.8%, but ARAG Full jumps all the way up to a massive 94.5% accuracy. And what's even more impressive, even just a naive version of ARAG, one that was given autonomy but only a single search tool, beat out those complex graph-based methods. It really proves that autonomy itself is a massive performance driver.
And the efficiency data reveals a highly counterintuitive finding. You would probably assume that to get that 94.5% accuracy, ERAG must be pulling in a literal mountain of text, right? It's actually the exact opposite. ARAG gets its massive accuracy boost while retrieving significantly fewer tokens than older methods. GraphRag pulled in over 8,700 tokens to get its 82.5% accuracy. ARAG Full only needed about 2,700 tokens to hit 94.5%. By giving the model those hierarchical tools, it precisely targets what it needs, completely avoiding the noise and token bloat of irrelevant content.
Finally, Section 5, the future of AI agents and test time scaling.
The paper highlights a massive 25% performance improvement simply by scaling up test time compute. In simpler terms, that means giving the model a little more time to think and execute search steps before it's forced to spit out an answer. And this is an absolute game changer. Because ARG lets the model make its own retrieval decisions, just increasing the maximum steps it's allowed to take to search, read, and evaluate directly scales up the performance. The system naturally gets better the more computational resources you throw at it during that test time. But we also need to look at when things go wrong, because analyzing these failures reveals something fascinating about where the frontier of AI research is heading next. In older RAG systems, failures mostly happen because the system simply couldn't find the documents. But looking at the breakdown of failures on datasets like Musiki, 82% of errors are now reasoning chain errors. Digging deeper, the vast majority of that is entity confusion, meaning the model reads the chunks containing the correct answer, but gets distracted by other information. So the RAG bottleneck has officially shifted. It's no longer about finding information, it's about reasoning about it accurately once it's found.
The researchers summarize their findings perfectly, and it is truly the crux of this entire paper. When they tested this framework on an older model like GPT-4o Mini, ARAG was great. But when they upgraded to the smarter GPT-5 Mini, the gap between ARAG and traditional methods widened significantly. It confirms that by giving the AI autonomy, the overall system's performance will naturally skyrocket as the underlying frontier models get smarter. The better the AI gets at reasoning, the better it actually gets at searching.
So I want to leave you with this final thought. For years, we've been trying to build better, more complex tracks for our AI to run on. But RAG proves that the real solution might just be taking the AI off the tracks entirely. If we are already breaking benchmarks and cutting token usage in half by simply letting the AI choose how it searches hierarchically, what kind of unimaginable breakthroughs are waiting for us as these models become even more advanced? Thank you so much for exploring this with me today, and keep questioning the frameworks we rely on.